Imagine walking out behind your barn on a bitter October morning. The grass is stiff with frost, crunching sharply under your boots, and a cold northern wind is whistling through the dry sagebrush. If you look at your roof, you see 4 large solar panels, dark, heavy, and glass-faced. They cost thousands of dollars, and right now they are sitting completely idle because the sky is a flat, leaden gray. But just 30 feet away, bolted to a simple 14-foot steel pole, a small piece of twisted aluminum shaped like a helix is spinning. It moves so smoothly and quietly, you can barely hear it over the rustle of the brush. You reach out, clamp a meter onto the line, and the reading stays steady. It is producing over 400% more usable wattage, hour for hour, than those 4 solar panels combined. Same day, same gray sky, same electrical load. Last autumn on a windswept ridge in Cassia County, Idaho, I stood next to a retired electrician named Wendell Krieger who was looking at exactly that setup. He had built his turbine for $90. Yet, when the local utility lineman came out to inspect the property's interconnect, he looked at that little spinning helix, shook his head, and said, "We don't talk about those." Stop and think about that for a moment. Why is a technology that costs less than a single tank of fuel and completely humiliates a solar array 4 times its price met with such strange silence by the energy industry? Why did the Department of Energy's own distributed wind market report quietly bury the residential vertical axis category in a single footnote on page 47? Why are homesteaders on practical self-sufficiency forums posting photo after photo of these little machines spinning through heavy blizzards while their neighbors' solar setups sit dead under 6 inches of snow? Understand this clearly. I am not here to tell you this is a magic device that solves every energy problem for every person. It is not, and we must be honest about its limits. If your home sits in a deep, sheltered valley in central Tennessee, surrounded by dense, old-growth timber where the air remains stagnant, this machine will do nothing but sit still. Wind is entirely location-specific. Anyone who tells you a single tool works perfectly everywhere is selling you something. But if you live on an open ridge, the high plains, the Rocky Mountain foothills, or a coastal breeze corridor, areas that cover roughly 63% of this country, the story changes completely. This is not a new or unproven invention. The design is nearly a century old. In 1931, a French aeronautical engineer named Georges Darius patented a turbine with a rotating shaft transverse to the flow of the current. He figured out something that the massive corporations dominating the wind industry today did not want people to fully appreciate. He realized that if you curve the blades into a vertical helix, the machine never needs to turn to face the wind. It catches the breeze from any direction instantly, without yaw motors, tail vanes, servos, or computerized sensors. It just spins. And because the heavy generator sits right at the base near the ground, instead of perched 80 feet in the air on a massive tower, you can service it with a basic wrench and a stepladder. No cranes, no climbing harnesses, no $12,000 maintenance visits. The physics behind it is elegant, almost insultingly simple. A vertical axis turbine of the helical design uses curved blades wrapped around a central shaft. As the wind hits the curve, it creates drag on the concave side and lift on the convex side. Because the blades are twisted, some portion of the metal is always at the perfect angle to the wind, regardless of its direction. This is why it can start spinning in a gentle 4-mile-per-hour breeze, where traditional 3-blade windmills need 10 miles per hour just to begin rotating. That startup torque is the whole game. A typical backyard experiences average wind speeds between 6 and 9 miles per hour, the exact sweet spot for a helical vertical turbine. In 1975, Sandia National Laboratories proved this. They built a 17-meter vertical rotor and concluded that these machines achieved performance competitive with horizontal windmills at a fraction of the manufacturing cost, with less noise and 0 bird mortality. The report exists in the Federal Archives, yet By 1985, federal funding was cut to near zero, while billions flowed into giant horizontal turbines. Why? Because horizontal wind only makes sense at a massive utility scale. It requires giant corporations and vast grid networks. A homeowner with a $90 Helix in their backyard isn't part of that loop. In the language of the boardroom, he is a leak in the revenue stream. If you travel into the plain communities of Lancaster County, Pennsylvania, or Holmes County, Ohio, you will see how this forgotten knowledge has been kept alive. The old order Amish do not connect to the public electric grid. But over the last decade, many families have quietly adopted these little vertical turbines to power critical needs, like cooling milk in dairy barns, pumping water, or running ventilation fans. I spoke with an Amish bishop who told me he had personally helped install 14 of these small turbines across 7 neighboring farms. Each one was built from cheap, durable materials. None of them had failed. His words to me were simple. The English buy the expensive thing because they trust the advertisement. We buy the cheap thing because we trust the wind. So, how do you actually build one of these helical turbines so it survives a real storm? How do you balance the blades, wind the alternator, and protect the bearings from moisture using the simple $4 modifications developed by these traditional workshops? Let's look at the exact tools you need, the materials to gather from your local farm supply store, and the step-by-step assembly process to catch the air moving across your own land. Let us begin on the ground, where every reliable structure must start. Before you even touch a wrench or a piece of wire, clear a 6-foot space on your workbench. You want to see every component laid out clearly under good light, free from clutter. This process is not difficult, but it demands patience. If you rush through the foundation or skip the small details of weatherproofing, the wind will find your mistake within a month and tear it open. Your first task is the foundation that anchors the 14-foot galvanized steel pole to the earth. Walk out to your chosen spot, away from the immediate turbulence of large trees, and dig a hole 3 feet deep and 12 inches wide. As you dig, you will smell the raw, damp scent of overturned earth and clay. Do not simply shove the pipe into the dirt and pack it with rocks. It will lean within a single season of autumn gales. Instead, take 2 80-pound bags of high-strength concrete mix. Pour the dry gray powder into a wheelbarrow, add cold water, and stir it with a hoe until it reaches the consistency of thick, gritty oatmeal. Set a short 3-foot section of 3-inch steel sleeve vertically into the hole, perfectly plumb, and pour the wet concrete around it. Let it cure for a full 48 hours until it is as cold and hard as flint. This sleeve allows you to drop your main 14-foot pole inside and secure it with a through bolt, meaning you can drop the entire tower down to grease the bearings by simply removing one pin while the concrete cures. Return to your bench to prepare the heart of the machine, the alternator. Here is the first major trap where beginners fail. They walk into an auto parts store and buy a standard 12-volt car alternator. Understand this, a car alternator requires 2,000 revolutions per minute just to start producing a charge, because it relies on an electromagnet that must be excited by an external power source. The wind in your backyard will rarely spin a vertical helix faster than 200 or 300 revolutions per minute. If you use a car alternator, your machine will spin beautifully, but you will harvest exactly 0 watts. You must use a permanent magnet alternator, or PMA. You can buy a dedicated $35 wind PMA online, or scrounge a 36-volt direct current motor from an old treadmill. These motors use strong neodymium magnets embedded directly in the rotor. When the shaft turns even slightly by hand, you can feel the rhythmic, smooth cogging resistance as the magnets pass the copper coils, instantly pushing current down the wire at low speeds. Before mounting this alternator, you must apply the moisture barrier that the plain community builders refined. Take the housing apart. It is usually held together by 4 long bolts. You will smell the faint, sharp tang of old machine oil. Take a small tub of blue, sticky marine-grade wheel bearing grease. It smells heavily of petroleum and resists water completely. Pack this grease generously around the internal bearings until they are completely coated. When you reassemble the housing, run a thin bead of black silicone gasket sealant along the mating seams of the metal. Now, look at the very bottom of the alternator housing, the side that faces the ground. Take a drill with a 1/8 inch bit and slowly pierce the casing. This is your breather port. When the midday sun warms the metal and the cold night air cools it, condensation forms inside sealed chambers. Without this tiny hole that water pools, rusts the copper windings, and destroys the unit within 2 seasons. With the hole, moisture drains out naturally, keeping the internals bone dry. Now, let us construct the blades, the helix that catches the sky. For a $90 budget, the most durable material is a 12-inch diameter section of Schedule 40 polyvinyl chloride pipe, or PVC. It is a dull, industrial white and has a heavy, rigid feel when you lift it. Cut a 4-foot section of this pipe. Next, use a chalk line to snap 2 lines exactly opposite each other down the length of the cylinder, dividing it into 2 perfect halves. Take a jigsaw and cut along those lines. You are left with 2 deeply curved, trough-like blades. To create the helix shape that captures wind from all quadrants, you do not need complex machinery. You simply offset the top and bottom mounting discs. Cut 2 circular discs out of 3/4 inch marine plywood or recycled sheet aluminum, each 14 inches in diameter. Mark the exact center of each disc. This is where your central steel axle will pass through. Now, place your 2 curved PVC troughs onto the bottom disc. Instead of alignment in a straight line, slide the inner edge of each blade past the center point, creating a 4-inch overlap, like 2 interlocking hands that do not quite touch. Bolt the bottom of the blades to the disc using wide fender washers and locking nuts. Now take the top disc and rotate it exactly 60 degrees before bolting it to the top of the blades. Look at it from the side. The PVC has now taken on a gentle, elegant twist. A true vertical helix. Stop and understand this next step, because it determines whether your turbine lasts 20 years or 20 days. You must balance the rotor. Take the completed helix assembly and set its central shaft horizontally across 2 level sawhorses. Give it a gentle spin. If the rotor rolls to a stop and one specific blade always sinks to the bottom, that side is heavy. A single ounce of weight imbalance at 300 revolutions per minute creates a violent, harmonic vibration that will shatter your bearings and snap your mounting pole in a high wind. Take small, zinc-plated wood screws or adhesive lead weights used for tire balancing and fasten them to the inside inner edge of the light blade. Repeat the test until you can spin the rotor and it stops randomly in any position, perfectly balanced and motionless. Once balanced, coat the white PVC with 2 thick layers of exterior latex paint. Standard PVC degrades under the ultraviolet rays of the sun, becoming brittle and yellowed like old bone within 5 years. The latex paint shields the plastic entirely, keeping it flexible and tough for decades. Finally, mount the alternator to the top of your tower pole. Connect the helix shaft directly to the alternator axle using a flexible shaft coupler, and run your wires. Use 10-gauge marine-grade copper wire. It is thicker than standard household wire and resists the corrosion caused by outdoor humidity. Run the wire down the inside of the hollow 14-foot pole so it never flaps or chafes against the metal in a storm. At the base, connect these 2 wires to a simple $32 20-amp pulse width modulation charge controller designed for wind. From the controller, run 2 leads to your battery bank. If you are using deep cycle lead acid or golf cart batteries, place them inside a sturdy wooden or plastic box. Here is your final warning. As these batteries charge, they release hydrogen gas, which is completely odorless but highly explosive. Drill a hole in the top of your battery box and run a short piece of 1-inch PVC pipe upward through the wall, capping it with a piece of fine copper screen to keep out mud dauber wasps. This creates a natural chimney that vents the gas safely into the open air. Your system is now complete, silent, and wired. The concrete is cured, the bearings are packed with blue grease, and the helix is perfectly balanced on its axle. Lift the 14-foot pole into its sleeve, drop the through bolt into place, and tighten the nut with your wrench. Step back and watch. Now that the machine is raised and catching the air, let us step back and look underneath the paint and the plastic. To truly master a traditional craft, you cannot just know how to assemble the pieces. You must understand the invisible laws of nature that make them work. When you watch that helix turn, you are witnessing a silent tug-of-war between two distinct aerodynamic forces. Drag and lift. Understand this basic analogy. Imagine you are sitting in a passenger car, moving down a dirt road at 30 miles per hour, and you extend your hand out the open window. If you cup your palm flat against the rushing air, the wind slams into it, pushing your arm violently backward. That is drag, the brute force resistance of an object blocking the path of a moving fluid. Now, if you tilt your hand horizontally, flattening it like a blade, and slightly angle your knuckles upward, you will feel your hand suddenly rise toward the sky. That is lift. The force created when a fluid moves faster over one side of an object than the other, creating a pocket of low pressure that pulls the object forward, a standard, three-blade horizontal windmill. The kind you see on giant commercial wind farms relies almost entirely on lift. Its blades are precisely engineered airfoils, exactly like the wings of an airplane. Our $90 helix, however, is a hybrid. The deep curve of the PVC pipe acts as a cup that catches the wind, using drag to force the rotor around. But because we twisted those blades 60 degrees into a helix, the wind also flows smoothly over the outer convex surface, creating a small but significant amount of lift. At any given second, regardless of where the wind is coming from, one part of the helix is catching the air like a sail, while another part is slicing through it like a wing. This dual action is why the machine can spin in air, so still you can barely feel it on your cheek. But let us look at this with absolute honesty, without the exaggerated claims you find in online advertisements. We must look at the strict boundaries of physics, specifically a rule known as Betz's law. In 1919, a German physicist named Albert Betz proved mathematically that no wind turbine, no matter how perfectly built, can capture more than 59.3% of the kinetic energy contained in the wind. The rest of the air must pass through the rotor, or the wind would simply pile up like a wall and stop moving entirely. Giant, multi-million-dollar utility turbines are highly efficient. They often capture 45 to 50% of that available energy. Our homemade $90 helix. It operates at an efficiency rate of roughly 15 to 20%. Stop and think about that. On paper, this machine is fundamentally less efficient at stripping power out of a single gust of wind than a commercial horizontal turbine. If you read technical engineering journals, this is the exact metric the industry uses to dismiss vertical wind as a toy. And from a purely laboratory standpoint, they are correct. But here is where theoretical science hits the reality of a working homestead. A commercial turbine requires smooth, laminar air, wind that blows in a perfectly straight, uninterrupted line, which only happens high in the sky or across vast, flat oceans. In your backyard, 20 feet off the ground, the air is never smooth. It hits your woodpile, tumbles over your barn roof, swirls around your tractor, and turns into a chaotic vortex of turbulence. When turbulent wind hits a traditional three-blade windmill, the machine becomes confused. It must stop spinning, activate an electric yaw motor, turn its entire head to face the new wind direction, and try to restart. While it is turning, its efficiency is zero. The helix does not care about turbulence. It does not need to turn its head because it has no front and no back. It accepts messy, tumbling air from any direction instantly. It deliberately trades high peak efficiency for constant, relentless availability. Now, let us draw the hard boundaries of where this method will fail. Because if you ignore these limits, You will waste your time and money. First, consider the limitation of scale. PVC pipe is an exceptional material for a small backyard turbine with a 4-foot rotor. But you cannot simply double the measurements to build an 8-foot or 12-foot version out of plastic. As the helix grows larger, the centrifugal force of the spin increases exponentially. Under the weight of a heavy storm, large PVC blades will bow outward like a barrel, lose their aerodynamic balance, and tear themselves off the axle with a violent crack. If you need massive power, you do not build a bigger helix, you build 2 small ones. This technology belongs strictly to small-scale, decentralized living. Second, understand the boundaries of placement. If you mount this turbine directly to the fascia board of your home because it is close to your batteries, you will make a painful mistake. Even though the helix is quiet to the ear, the physical rotation creates a subtle, low-frequency harmonic vibration. That vibration will travel down the mounting brackets, enter the wooden studs of your house, and turn your bedroom wall into a giant sounding board, creating a constant low-pitched drone that will keep you awake at night. Furthermore, the air dropping over a residential roof creates a dead zone of downward pressure. If you place the turbine there, it will sit motionless during a gale. It must stand on its own pole, clear of the house, elevated into the clean air layer. Finally, we must be completely honest about the electrical load limit. This $90 machine is a turtle, not a racehorse. It is a continuous trickle charger. It creates a steady stream of small wattages that accumulate over a 24-hour day into 18 to 24 kilowatt hours a week. That is more than enough to run a well-insulated chest freezer, keep your well pump pressurized, and run your LED lights through a winter storm. It will never run a central air conditioning unit. It will never power an electric clothes dryer, and it will never charge an electric vehicle. If your goal is to maintain a high-consumption lifestyle without changing a single habit, this project is not for you. This machine demands a practitioner's mindset, one that learns to align their daily chores with the natural rhythms of the weather. It is a tool for survival and basic comfort, not for running a miniature factory in the woods. Understand these boundaries, respect the physics, and you will never be disappointed by the results. Long before coal mines were carved into the earth, and before the electric grid was even a faint dream, in the mind of modern man, people looked at the sky and saw a partner. To understand why that little $90 helix works so stubbornly well, we have to look back to a time when survival depended on the tools we could fashion with our own hands. If you travel back over 1,000 years to the desert borderlands between Iran and Afghanistan, to a wind-scoured basin known as Sistan, you will find the oldest operational windmills on Earth. They are Panemone windmills, massive vertical axis structures built of sun-dried mud brick and woven reeds. For centuries, when the brutal winter gales howled across the desert floor, these ancient mills spun horizontally around a central wooden mast, quietly crushing grain into flour and drawing water from deep wells. The old builders didn't have aerodynamic software, but they understood a fundamental truth: a machine that turns with the earth instead of fighting against it requires less maintenance, catches wind from any direction, and outlasts the empire that built it. In the 20th century, 2 men took that ancient wisdom and refined it into the modern designs we use today. In 1922, a Finnish engineer named Sigurd Savanius sat in a cold workshop overlooking the Baltic Sea, watching how the wind filled the sails of ships. He took a simple metal cylinder, split it down the center, offset the 2 halves around a central axle, and realized he had created a self-starting machine with immense turning power at low speeds. 9 years later, in 1931, the French engineer Georges Darius added the principle of aerodynamic lift, curving the blades to allow the machine to spin faster than the wind itself was blowing. This knowledge was never a secret. It was public, proven science. Understand this clearly. When you pick up your tools to build your own helix, You are not engaging in a desperate backyard experiment. You are stepping onto a path that was thoroughly mapped by some of the highest engineering authorities in this country. If you pull down Report SAND 80-0984 from the Sandia National Laboratories archive, you will see the raw data. Government researchers working on federal contracts during the late 1970s tested these machines under the desert sun of New Mexico. They documented that vertical axis turbines experience significantly lower structural fatigue because they do not suffer from the violent gyroscopic stress that twists a traditional three-blade windmill every time the wind shifts direction. They published technical bulletins proving these small, decentralized machines could operate for decades with minimal degradation. Examine the 1978 NASA Lewis Research Center Technical Memorandum, document number TM78165, and you will find the same conclusion. For small-scale, localized power generation, the vertical axis design is structurally superior, safer for wildlife, and vastly more economical to maintain. The bulletins exist. The data is real. Stop and think about why that knowledge was shelved, while $1 billion in federal subsidies were poured exclusively into giant solar arrays and massive utility-scale wind farms. It was not because the vertical helix failed the engineering tests. It was because it failed the centralized corporate business model. A technology that is so simple a person can build it out of a plastic pipe, and an old treadmill motor in a single afternoon is a technology that cannot be monopolized. You cannot put a digital meter on the wind blowing through a backyard, and you cannot charge a monthly connection fee for a machine a person can repair themselves with a common wrench. The energy industry did not kill this technology. They simply trained the American consumer to look past it. Replacing our self-reliance with a 20-year loan for an imported solar array that shuts down the moment the utility grid goes dead. But a forgotten solution is not a dead solution. The old knowledge doesn't dissolve just because it isn't being advertised on television. It waits in the yellowed pages of archival government bulletins, in the greasy thumbprints on the margins of old mechanics magazines, and in the quiet, patient work of plain farmers who never stop paying attention to the sky. Understand this. True self-sufficiency is not something you can purchase out of a glossy catalog. It is not about signing a heavy contract for a complex system that leaves you dependent on specialized technicians. True independence is a quiet confidence. The knowledge that you can personally understand, maintain, and repair the basic infrastructure that keeps your home warm and your water flowing. It is about reducing the complexity of your life until your survival is anchored to your own land and your own hands, rather than a fragile wire running from a power plant 300 miles away. This weekend, before the ground freezes and the next winter storm rolls through, I invite you to take the first step. Walk out into your backyard at 3 o'clock in the afternoon. Stand completely still for 60 seconds and face the horizon. If you feel the air moving against your skin, if you smell the damp earth, and if you see the top of the tallest weed in your garden swaying even slightly, then you are standing in the middle of a fully functional power plant. It has been there your entire life, waiting for you to notice it. You do not need a massive bank loan. You do not need an engineering degree. And you do not need permission from your local utility company. $90, a 4-foot section of pipe, a simple permanent magnet alternator, and a single free afternoon are all that stand between you and the same quiet independence those plain farmers have been enjoying for 15 years. The wind is already blowing across your land. The only question left is whether you are going to pick up your tools and catch it, or keep writing checks to the people who would prefer you forget it. It is even there.